right, let's get started. So from now until the end of the semester, we're going to put a heavy focus on what's called supervised learning. So I'll talk about what that is. And then we're also going to talk a little bit about unsupervised learning, which is an alternative. But we're not really going to do it mostly in this class, so I'll just skip over that real quickly and just mention it as we go along. Then I'll cover some terminology so that we can start talking about this stuff. And I'll quickly mention something about overfitting and underfitting. And then we'll do some problems, and I'll point out where each of those things comes up in the problems. So I think the best way to start is to have a motivating example. Why do we care about machine learning, and what does it do for us? And so what machine learning lets you do is it lets you make decisions and classify things or come up with estimates given some data. So for instance, if I was a housing vendor in San Francisco and I wanted to know how much this property costs, I might look at properties that are similar to it in terms of square feet or location or number of bedrooms, and then off of that data come up with, and their prices, I might come up with an estimate for this price, right? And so here's an example of maybe a chart you could see at a hospital. So this is patient age on this axis, and then we have tumor size on this axis. So these are what are called our input vectors or features. So these are features of one of our patients. And we're going to try to figure out, we're going to try to classify them. Okay. So with this data right here, I've just drawn a bunch of dots where some patients are on this graph. There's not really much we can say. We can say, well, I guess without knowing what if these patients had, disease or if they had cancer or something like that, without knowing that, all we can really say is, well, there seems to be two sort of groups, right? There seems to be this group over here, and there seems to be like this group over here. That's about as best we can do, right? And so this is unsupervised learning, and what I mean by unsupervised is there's no one helping the algorithm along and giving it some examples where, yeah, this person was sick or this person was healthy. There's none of that help, we just have these points, so that's unsupervised. Now this problem becomes a lot easier if I start telling you this person came up negative for cancer, negative, negative, negative. This was positive, this one was positive, positive. And these ones were positive, 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 positive. And then there was one negative in there. Now it becomes much easier to tell what's going on. You see a bunch of these negatives in this group, and you see a bunch of these positives and maybe one or two negatives in there. Maybe one or two positives in here, and it becomes a lot easier to tell what's going on. Now if I asked you, what about a new patient that just came in, and they're right here, what would you say about them? What would you tell them? How would you prescribe medication for them, right? And so in this example, you can see there's a lot of people that are showing up negative for cancer here, and because that person is over here, presumably you might say, well, it's a pretty good guess that they don't have cancer. Now if someone's like, let's say a new person's right there, you might be worried and prescribe them something, right? It's a little bit of a not real example because I think you'd probably be a little more cautious if you had a hospital than just not doing anything. But you could imagine how this is extrapolated to something like Netflix. You might have more than a two-dimensional feature space. You might have like, is it an action movie? Does it have Tom Hanks in it? Is it a documentary? Is things like that? And so that feature space, I could say, for instance, I really like action movies, and that's like an example I'm giving it. And now I might be able to think, well, this new Tom Hanks action movie is really good. Maybe you would like it. And then I might tell it, I don't like that one. And then it might be able to learn like, well, maybe he doesn't like Tom Hanks. And then it'll kind of learn as we go, right? So that's what the algorithm's trying to do. Awesome. So there are a couple different strategies of making sense of this data. And we're going to talk about two of them today. And so specifically, we're talking about supervised learning algorithms. So forget that notion about having unclassified points. We're only talking about classified points. So what I mean by classified, just to say again, is that they're already labeled. We have some examples that are already labeled with their output or their classification or what we're going to describe them as, right? Awesome. So these two things that we're going to talk about are going to be ID trees and k-nearest neighbors. So those are two learning algorithms. But before we do that, I'll talk a little bit about terminology. So I've already mentioned a couple of these words. So there's inputs, which are the features. So the inputs are going to be, I like to draw them as a vector. A vector, if that's scary for you, because when I first saw this, it was scary for me because I'd never taken like linear algebra. It's just like a big list of these things. And this could be, in other classes, you might call this like X, Y, and Z for 3 dimensions. These are just, there's an n-dimensional thing here. So this might be like how tasty the hamburger is, how much tomato it has, how much ketchup it has. And then the output might be like, is it from McDonald's or not? right? So you want to classify it. And so the classification is usually described as a Y. And so you have X at this input space, and you have Y that's the output or the classification, okay? So we're trying to guess this given this, all right? Any questions about that so far? All right. So a training set is like something we have here. This isn't like the entire universe of every patient in the history of man who's ever had gone to the doctor or anything. This is just 100 people I picked at random, right? Maybe I didn't pick them at random. It's just 100 examples. And so that's our training set. So we're going to try to extrapolate and try to come up with some cool way of guessing the outputs for things we don't know about, given our examples. So this is like our training set, right? So a training set is like a bunch of these XY pairs, right? So there's a bunch of these. And so the way I like to draw it is because I already used the little suffix to mean like the first part of X, the second part of X, and the third part of X. The way I differentiate that from like the training example is I like to put the number of the training example in like parentheses up here. So this isn't like exponent, this is just numbering the examples. And you'll see this notation a lot in other schools and especially in other classes here. I don't think this notation is really used in 034, but I like to differentiate these. Right, so this one means first training example. This one means for this training example, the first part of the X. Right, so this might be tastiness or something. Awesome. Okay, cool. So that's the terminology, and then we'll talk lastly about overfitting and underfitting. So I'm just going to say it real quick right now, and then we'll talk about it more in detail after. This stuff, you can see it's not really perfect data. It's not like all of these things are cancer-free and all of these guys have cancer. There's a couple outliers in there. You know, there's one guy in here that does have cancer, and there's one guy over there that doesn't. So it's not like you can't just separate the data perfectly, right? And so there's some outliers. And what we care about with overfitting and underfitting is making sure that we generalize well. And what I mean by that is we're making our algorithm from this training set. We don't want this training set to so heavily influence our decision of our learning algorithm that we're only going to get things right from the training set, but like a new thing, we're going to get it wrong. Another way of saying that is we don't want to take outliers too seriously, okay? You can imagine if we had like 1+ in this whole group, and we were right here, maybe like a cool thing to do would be like, oh, just diagnose him the same as the nearest person. And so you might diagnose him as having cancer, even though he's still within this group. So you're giving a little too much credit to that one guy. Okay, so that's like overfitting. Underfitting is the opposite. You're not giving credit enough to the people, to the training sets, to the training points that would give you a good decision. And so now you're making like a way too generalized decision. Okay, so these two things are pretty hard to understand. They're sort of intuitive, but then they have like really rigorous mathematical definitions. And so it's like not as intuitive later on, but we'll talk about those in an example and it'll become clear what those are. So if those don't make sense to you right now, don't worry about it. All right, so just a quick little intro. And now let's do a problem. So I'm going to leave this picture up here. And so I'm going to talk about the first strategy that we're going to use, which is ID trees. Now what ID trees is going to do is it's going to try to separate the space by drawing straight lines, like perpendicular to the features, okay? So these features, patient age and patient tumor size. You might think like, you know, a cool way to separate this would be to draw a line like this and draw a line like that. And anything down here is cancer-free, and anything down here is cancer-free, and anything down here is cancer-free. But up here they have cancer, right? Given our training set, that seems to make a lot of sense, right? So you might want to divide the space up like this. So the way that ID trees divide the space up like this is they ask questions to separate things from left and right. So for instance, tumor size. This might be like some X tumor size, right? Let's not use X because X is used in, let's do TS for tumor size. This might be like a threshold that we pick and we ask, the question we ask is the tumor at least this big? If it's not, we put it on the left, and if it is, we put it on the right. And then we'll be able to classify it. So you can see, if it's lower than this tumor size threshold, we don't even have to ask any more questions. For this training set, we can just say, it probably doesn't have cancer. But if it's greater than that, we might have to ask another question. And now how are we going to divide the space between top and bottom? Is we can use a question about the patient age. We can say, is the patient at least PA? And if they're greater than that, we might say, okay, their tumor size is bigger than TS, and their patient age is bigger than PA, then they might have cancer, right? So this is how we're going to divide up the space, all right? So here's the data we have. So this over here, this 1, 2, 3, 4, 5, 6, are just for our convenience, so I can refer to these points, so I don't have to like point to them. I can just say like, oh, point number 3, like this thing, right? So this is not part of like training set or output or input or anything. This is our y. This is what we're trying to guess, whether it's an angel or not. And I'll talk about the question in a little bit. And then these are our features, the shape, height, and material of a statue. And so this question comes from like a Doctor Who reference or something, where there's like angels that are statues, and then if you touch them, you like travel back in time. I don't know. I've never seen Doctor Who, but they're trying to avoid these angels. So they're trying to use these facts to when they get a different angel. These 6 obviously they know, but when they get like a 7th person who they don't know what it is, but they might have some information down here, they might be able to make a guess as to whether it's an angel or not, given this data. All right. So let's do that. So for ID trees, what we're going to try to do is we're going to try to split it up. Now in this picture, it's really easy to see how to split it up. If you have to draw only straight and vertical lines, perpendicular to the features, I think a lot of you would come up with this cross, right? You want to get rid of that thing, so you need to put a little box around it. Okay, well that requires 2 lines like that, right? Pretty obvious. But now when you have something like this, it's not so obvious, especially because we haven't graphed this. How are you going to draw those lines? And so with this, we have a cool strategy that comes from information theory, which just means we're going to use an information theory equation, which we don't really have to understand. But it's this thing. It's going to be scary. Yeah, so that thing. Okay, great. What does that even mean? The only thing that this is telling us is this is our metric that we're going to use for where we draw the line. So we're going to choose the question, right? So when previously we had asked the question like, is it greater than the patient's age or is it less than this patient's age? Now what we're going to do is we're going to choose the question we're going to ask based on this metric. So we have a couple candidate questions. We could ask, is its height bigger or less than 7? Right? We could ask, is it a human or an animal? What's its shape? Or we could ask, what's its material? Right? We could also ask other things for height, right? We could ask like, is it greater than 2? Is it greater than 100, right? There's a lot of things in here because this is like a continuous variable. For these 2, these are not continuous, these are discrete. There's only a set of options to choose from, so it's a little more constrained. So let's do what the problem asks and try to choose the best question for our ID tree. And so the way the ID tree is going to work is we're going to have question, and it's going to separate our training examples into 2 camps, things that fall on the yes and things that fall on the no branch. So we can say like, is it a human? And we might say like human, and we might say animal. And then some examples will end up over here, just based off that data. And some examples will end up over here. And then if we've perfectly separated them, we're done. But if there's still some separation to be done, we take that subset and we keep asking questions until we fully separate it. All right? So I'm going to run like through 1 or 2 of these, and it'll be really clear what I mean. So the way I'm going to choose my question is with this. So let's see the 3 candidate questions that they give us. They call them tests instead of questions, but same thing. So they say, test 1. Material. Okay, so let's consider the material test, okay? So right now, none of these things have been classified by our ID tree yet. So the way we're going to start is by having all of our examples that are going to be classified by this material box. So you can imagine all of them are coming in here, and now they're going to either go that way or that way. And so there's, what are the 2 things? Stone and copper, right? And this is a convention. And a lot of these problems, when we only have 2 classifications, you can see we only have angel and not angel. Pluses and minuses are really common to use. You can use triangles or circles. It's just symbols. They don't mean anything. But plus or minus are just conventions. So I'm going to use those. So we can say, like, for instance, example 1 is stone, and it's an angel. So I'm going to put stone. I'm just going to put a little 1 there so I remember it came from 1. 2 is stone, and it's an angel. 3 is copper, and it's not an angel. 4 is copper, and not an angel. 5 is stone, and not an angel. Stone, that's 5, not an angel. And then the last one is copper, and it is an angel. All right, so that's just how this test material, is it stone or copper, would separate our data, our training set. Okay. Okay, cool. So now, how good is this of a separation? It's kind of hard to say. You can kind of look at it, and just by inspection, it's not that great. Like, we're not getting great separation. We're still getting a pretty mixed bags on both left and right. It's not that great, but maybe it's better than anything else. But what if you get another test that's like, it's a mixed bag too? Like, how do you compare those two things? So that's where this thing comes in. This gives us like a mathematical number for comparison between two tests. And so let's use it right now. So what we're going to do is we're going to do this equation for each branch, and then we're going to sum it over like total, over the branches. But we're going to normalize this thing with like total over branch value or something. Anyways, this is just an equation. There's a better one that I'll write up in a little bit, but it'll be really easy what I'm doing. So all I'm going to do is I'm going to look at the left side. I'm going to see this branch, right? Branch left. And I'm going to say, what's the probability that if I'm in branch left, just considering my training data, that I'm an angel, right? And so there's 2 out of 3 of them there. So really simple, 2/3. So I say, okay, for the left, for stone, so let's do, this is stone. I have minus the probability of being an angel, which is 2/3, times the log base 2 of being an angel. So that's I'm summing over C, okay? So I've already summed over the angels. Now it's time to sum over the other classification, which is not angels. So now I do it over not angels, and I think it's minus the probability of being not an angel is 1/3, times log base 2 of 1/3, okay? So this is our disorder on this branch. This is what this metric is called. It's called the disorder. It comes from information theory. Not really important. We just use it. And so now we can normalize this by the weight that this branch has. And what I mean by that is that's the disorder of this set. But how much does this set matter compared to the whole thing? So how much it matters is just how many training points there are in here versus the total, which is 3 out of 6. So it's half, right? So I'm just going to weigh this by 1/2. Okay? And so this is the disorder that comes from this branch. Now let's do the same thing for this side. Now, if you can see, it's pretty much the same thing, except I've got minuses where I've got pluses. So it's just going to be, if I do it for, if this was the pluses and this was the minuses for the left, it's just going to be 1/2, because half of the points are in this branch. 1/3, if I'm in the right branch, there's a 1/3 chance I'll be an angel. Log 2, 1/3. Minus 2/3, I'll be not an angel. Log 2, 2/3. All right? And so now I have the disorder for this whole test. And remember, this disorder word, you don't have to know what it means. It's just a score for telling us how good this test is of separating the data. And what we want to do is we want to minimize the disorder. So it's kind of intuitive. If you minimize the disorder, you're maximizing the order. So we're ordering them, we're separating them based on what they are, right? So minimize the disorder. So let's minimize this quantity. So, okay, for this test, that's the disorder. So let's look at a different test. Maybe it has a smaller disorder than we could care about. So the next test that we have is, what shape is the statue? So let me just write down this disorder here. And you can see they were both 1/2 and I was summing them. So it's the same thing if I sum them as just multiplying them by one of them by 2, right? So that's me summing them. Okay, did that confuse anyone, what I just did there? Okay, cool. Awesome, so there's the disorder for material. So let's try a different test. So 2 outcomes are human and animal. Again, really easy. Just going to go through them again. And now we're still choosing between these tests. So we're choosing between which one would filter out the whole data set the best. So we're still considering the whole data set. The fact that we've sorted them here for test 1, we're not using that for test 2. Okay, test 2 is starting clean because we haven't chosen anything yet. So let's put everything through the shape test and see what happens. So we have test 1 is human and it's an angel. Test 2 is human and it's an angel. Test 3 is human and not an angel. And test 4 is animal and not an angel. Test 5 is animal and not an angel. And 6 is human and it is an angel. All right. So without even computing the disorder of this thing, can you guys tell which one of these will have a lower disorder? Which one is a better test for separating the data? Bottom one? So why do you guys say the bottom? I guess this is pretty obvious, right? Like, the minuses are all separate here. We're done asking questions. We can classify this side of things right away. We can say, if you're an animal, you're not an angel, right? If you are, you're pretty much an angel. There might be another question we can ask to try to get this point separated even further. But this looks pretty good. So let's see if our intuition was correct and compare the disorders between these two things, okay? So let's do the disorder of the left branch. So what's the probability of being an angel on the left branch? Yeah, so just 3 out of 4 of these, right? So we have 3/4, log base 2, 3/4, right? Minus, because there's always a minus in front. And now let's do being not an angel. Well, that's just the reciprocal of that, right? Or the thing that adds to 1 with it. You guys know what I mean. 1/4, right? And then I've got to weigh this thing, because this branch isn't the only branch we care about. So we've got to weigh this branch by how much it should matter. And so how much does it matter? 2/3, right? 4 out of total 6. So 2/3. Okay, now let's do the right branch. Okay, so what's the probability of being an angel on the right branch?
1. Not 0.
0, right?
Yeah.
So no component for the angel part. How about for the non-angel part?
-1.
Okay, so actually I'm just going to write this out because you're right, but I'm just going to write this out so that it's very clear how this thing is, how separating things means a low disorder in terms of that equation. So I'm just going to write it out. So this branch is going to be weighed by 1/3 minus the probability of not being an angel, which is 0, times the log base 2 of 0, minus, and then now we have the probability of being not being an angel. So many nots here. Okay, so 1 log base 2 of 1. Now, can anyone tell me what this expression comes out to be? 0, right? So log base 2 of 1 is 0. So this part is 0. This is being multiplied by 0, 0. This whole thing is 0. So you can see that because we have the probability multiplied by the log, if either the probability is 0 or 1, this whole term becomes 0. Okay? And so you can see it works out in our favor here because when we've totally separated things on the right branch. We only have one classification. We'll get the disorder to be 0, which makes a lot of sense. We've totally ordered the right side. Disorder is 0. So we get that. So that falls in line with our intuition. So that whole thing is 0. And now we'd have to compare this thing to that thing. And just because of our intuition, we can see it's better. But if you wanted to, you could plug this into a calculator and see that this is actually a lower number. So you could evaluate it. And so you could think shape is a better test than material for separating the data. And now we can do the last test that they want us to consider. So that's the disorder for that guy. Now I'm going to do the last test over here. All right, height less than 6 feet. Yes, no. So let's do it again. Whole data goes through. You see the first one is not less than 6 feet, and it's an angel. You see the next one is, and it is an angel. You see the next one is, wait, did I do that right? Yeah. It's not, and it is an angel. It's not an angel. Oops. Not an angel. Then we see the fourth one is, and the fourth one's not an angel. The fifth one is not, and it's not an angel. And the sixth one is not, and it is an angel. So what do you guys think of that? Definitely not better, right? What were you gonna say?
How did you pick 6?
Oh, they gave us this number.
Oh, okay.
They said these are the 3 tests that they wanted us to compare.
Okay.
Yeah, you're right. There is a genre of questions that is at X or H less than X, and you get to pick X. They picked X for us this time. Okay, cool. Is that cool with everyone? All right, so this one looks pretty terrible. Both sides are like exactly like still mixed, like 50-50, which is really bad. So we could compute the disorder, so let's just do it real quick. So we've got half of them. So we've got, first of all, this branch is worth 1/3. And we've got half log base 2 of a half minus a half log base 2 of a half. It's this branch. And then I'm going to add that with 2/3. And now we've got the same thing, except I'll write 2/4 just so it's really clear where these numbers are coming from. And I'll write, just in case anyone wanted to see those numbers where they came from. Okay, there's the disorder for that branch. Anyone spot any mistakes? I think that's right. Okay, we could plug this into a calculator, and you could see that it's actually bigger than this number, which makes a lot of sense intuitively. That thing's not really doing any separation for us. This thing is. So what we're going to do is we're going to pick test 2. That was the one. All right. So now let's start building our tree. So we've picked the first test in our tree. So our tree is going to start looking like sheep. Animal. Now, what happens if we go to the left branch? Can we give a pretty solid classification, or is there still some separation to be done? Yeah. So there's just one guy, but let's just still separate it. So this work to be done, so I'll just put it to do here. Okay, what about the right side? It's like totally separated, only minuses. So we can just conclude, hey, if you go over there, you're not an angel. Right? And now we can look over here and we can say, okay, well, what's left over here? So we've got Q1, Q2, or +1, +2, -3, +4. Okay? So we've still got these things to separate. So let's try to separate them next. All right, so now it tells us, for subsequent tests, you may use tests with the following form: the shape, the material, or height less than any value you want to pick, right? So height less than x. So our candidate functions to order these guys are shape, material, or height less than x, and we get to pick this. Okay. Is there any one of these tests that you guys think we can rule out right away for ordering these guys further? The shape, right? If we ask it again for the shape, we're just going to get like all of them to the left again. So let's not do that. Okay. So now the next things we can pick are material or height less than x. So let's calculate the disorder for material. Okay. So here's material. But now we're not asking about the whole training set. We're not feeding the whole training set in. We're just feeding these guys into it. Okay. And so it's really easy. I can just look at this picture and say, okay, well, 1 is still being fed, 2 is still being fed in, 5 is not there anymore, 3 is still being fed.
3 + 6, now +4.
This one? Thank you. 6. There we go. Okay. So it's the same as if I had just taken this set, redrawn this, and started like seeing where those things went, but only considering 1, 2, 3, and 6. Right? So that's the picture I get. So now we can calculate the disorder. So we know we see this right away, totally ordered. This branch is 0, right? Plus, and then we've got half of the things over here. So we've got 2 out of the 4 total things over here. So that's our weighting factor. And we've got -1/2 log base 2 of 1/2 plus 1/2 log base. That's a minus. Okay. There's our disorder for the material test. For And then we can do the calculation for height less than x. And so now height less than x is a little weird because we can pick this x. So let's analyze it for all possible values of x. So what happens if I choose an x less than 2.5? So everything's going to be put on the right side. So it's not going to help us to order things at all. So let's not consider anything lower than 2.5 our minimum. And the same is true of anything greater than 305 our maximum. That's not going to help us sort anything at all. All right? So now it's interesting to choose values between these numbers. You guys see that? So that way we can separate them. So let's start, I just like starting in order. So 2.5 is our minimum, the next one's 7. So let's just pick something between 2.5 and 7. So how about height is less than 3, right? Same test, same results as height is less than 4, right? It's a little arbitrary at this point. So let's just do 3, just to see what it would look like. All right, can you guys help me out to plug these guys in? So 1 goes no, right?
Right.
Or yes, it goes.
No.
Oh, 1 goes no. 2 goes yes.
Right.
3 goes no. And 6 goes no. Okay. So the question is that better than this? And so you could calculate the disorder. Again, it's almost like you can look at this and be like, well, it'd be nice if this thing was over here. That would help us out. Oh, that's what this picture is, right? So this is better. Right? You could calculate the disorder. I'll leave that up to you guys to do. But I'll just leave it up there. So that's height less than 3. And now how about something between the next value, 7, and the next highest value, 8, right? So 7.5.
It's an animal.
Hmm?
Isn't 8 an animal?
It is, you're right. So we don't have to consider that. Thanks for that. Yeah, so we only care about these points. So the next highest value that we actually care about, it's not 8 because we already like classified that correctly, but 305. So you can pick any value between 7 and 305. Thanks. So that's 100. Right? Any number. Let's try that out. So we get yes, we got no, and I think the only one that goes to yes is plus 6, right? And then all the other ones go 1, plus 2, minus 3. And so again, is that right?
Opposite, isn't it? 'Cause it's
Oops. Fine, I'll keep it that way. But no. Wait. Yeah.
Right.
Yeah. Okay, cool. Right? Oops, switch the branches. Anyways, it looks pretty much like that, just flipped because I didn't flip it, but it'll be just pretty much that and flipped in terms of how well it orders. They're ordering things differently, right? Like T6 is by itself here, T2 or plus 2 is by itself here. Different things, but they give us the same disorder. And we already concluded that this thing was worse than that, so this thing's also worse than that. Right? So let's pick this as our next test, because this one's the best one. Okay, so now let's put that over here. So if it's a human, we're going to ask the next question, which is material. We're going to put stone, and we're going to put copper. And so for stone, we can just conclude angel. Right? No work left to be done. These are fully separated. And for copper, we have minus 3 plus 6. So how do we separate these two guys? Well, now it's pretty easy. There's only 2 guys to separate, so we can kind of just brute force this, or like not even look at anything and just be like, I want 3 and 6 to be different. How do I make that happen? Well, they have the same material, they have the same shape. The only thing I can do is height. So 3 and 6, maybe I'll do like height less than 8. That'll separate them, right? So I can just pick any number between those to separate these guys. So I can do something like height less than 8. Yes. No. And so if it's a yes, then it's not an angel, right? Because that's from, this comes from 3, and then from 6, it's an angel. Okay? And so now you can see we've made this tree from our training set, but now if someone else comes along who is 10 meters tall and is a human and is made of stone, we can go into our tree and ask it, well, it's It's human, it's made of stone. Oh, we don't even have to know what heights an angel, right? And so remember, this is our best guess. It's not necessarily right. This is our best guess given the data, all right? And so now they ask you, we've made this tree by minimizing disorder, right? You can make different trees by a different metric. Disorder tends to be a really awesome one, and if you take some more machine learning classes, they'll derive why you want to use that and all that. But you can already tell it has a nice property that when we totally order something, the disorder becomes 0. So we talk about that. So that's pretty nice. So now they have a different tree, and it says your friend made this other tree to try to sort these things. And so their tree looks like yes, no, shape, human, animal, angel, not angel, plus 300, yes, no, angel, material, stone, copper, not angel, shape, human, animal, not angel. Okay, so this is the tree that your friend came up with. And so they're asking you, okay, both of these trees actually classify all the training set points the same, right? But which one used the training set in a better way? And what I mean by that is when we get something unknown, which one has the higher chance of giving us the right answer? Okay. So which one do you guys think generalizes better? So generalize is another word for saying, we're only looking at these points when we make it. Let's generalize to any point. Let's ask what would happen for any point that we don't know about. Which one would give us better results? That tree or this tree? You guys have any thoughts about that? So a hint, this goes back to under and overfitting.
Yeah, I mean, it seems like the one on the right is overfit, right?
Yeah, so what do you mean by that? Can you explain that?
I don't know, it just feels like it.
That's great intuition. So immediately, without knowing anything, if you have something more complex, it probably means you're taking into account your data more serious, you're using it more. And so if you keep using it more and more and more and more, you're gonna build your solution totally based off of these, and it might not get anything else right, but it for hell sure is gonna get those 6 right. And so that's what they're doing. They're building something that's totally for sure gonna get these 6 right, but they're using that information so much, they're not gonna be able to generalize and get other things right.
Yeah.
Right? So that's already something you can see is if it's more complex, it's probably overfitting. That's all you needed to say for that question. Yeah?
The branch on the right kind of caters to one of your outliers.
Yeah, that's another way of identifying overfitting. Overfitting is when your outliers determine your resulting classification algorithm a lot. When they affect it a lot, then you're overfitting to those outliers. Underfitting is you're not even taking into account normal data and you're just ignoring that too, right? But you want to ignore the outliers. This is not ignoring the outliers, so it's overfitting. Okay? Does that make sense? Awesome. So that's all I wanted for that question. All right. Okay. So now let's draw this. So now let's talk about nearest neighbors. So again, these are supervised learning algorithms. So we're giving them training data. We're building an algorithm for determining outputs and classification, same word. And we're going to run it on some examples and see what does better. In this case, we didn't run it on anything, but they asked you to analyze what would happen if you ran it on some random input. So now we're going to do the same thing, but with a different algorithm for classification. So we've got this X over here, we've got W, we've got Y, we've got V, we've got C, we've got 1, 2, 5, 6, 7, 11, 10, so for nearest neighbors, what we're going to do is we're going to use our neighbors, and what I mean by that are the people that distance-wise are close to us to make our decision, okay? So you can imagine maybe we're trying to figure out what x is, and we know that 1 is an angel. Then we might, if we use nearest neighbors with k equal to 1, which is the number of neighbors we consider, then we're just going to assign it the value of its closest neighbor, which is 1, which is a. So we're going to say x is probably an angel, right? Now you could think, now we're going to see that when you use really low nearest neighbor values for k, you might be overfitting, and we'll talk about that in a little bit. But to make it a little better, maybe we can consider more than just the closest guy, maybe the closest 5 guys, or closest 3 guys. So let's do closest 3 guys. Maybe these guys are not angels. Then x, well, the closest guy's an angel, but the next two say he's not an angel. So with k equal to 3, we're going to take the majority of this set, and it's going to be not an angel. Okay? That's how nearest neighbors work. It's pretty simple. Pretty intuitive. All right. And so k could equal anything, but usually they pick odd numbers because usually you're classifying between 2 things, so it helps break ties. If you're classifying between like 4 things, like there's 4 possible classifications or 8 or whatever, like odd numbers might not really help you. But okay, so now what they've got is they've got these statues. So these are the ones that we wanted to this is a y, by the way. Okay. These are the ones we wanted to classify. And then we used 1 nearest neighbor. We used 3 nearest neighbors. And we also used 5 nearest neighbors to try to figure out what they were. And we figured out what they were, but someone erased some of these entries. So not angel, angel, don't know, don't know. Angel, don't know. Not angel, not angel, don't know. And we have not angel, angel, don't know, don't know. Okay, so hopefully my question marks aren't really hard to read. But what this is saying is when we didn't know what x was, and we knew what the values for 1, 2, 3, all the way up to 11, I think it is, were, whether they were angels or not. And with nearest neighbors, with 1, we saw that we thought x was not an angel. But with 5 nearest neighbors, we thought x was an angel. Okay? So someone erased some of these entries, and we also forgot which one of these 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 11 were angels or not. So now we're going to work backwards, and we're going to say, okay, we have the results. Now let's find out what the training points must have been to generate these results. Okay, so we're going to work backwards. So let's try for point 1, 2, 3, 4, 5, 7, 8, 9, 10, 11. Okay, so let's try to figure out what these were given this data. Does anyone have a good way to start? Okay, well, let's just start with 1. Can we tell whether 1 was an angel or not based on this data? So whose decision does 1 inform on this graph? X, right? It's really close to X, so it's probably going to affect X's decision. So let's look at X. Well, X, so who's the closest to X? Well, it is 1, right? So for nearest neighbors equal to 1, this 1 is going to have like the most, is going to have the only say as to what X is. Okay? And so when we said we're only considering X's closest neighbor, and when we only consider that, we chose X to be not an angel, which means 1 must have been not an angel. Okay? So we can do it again, and you'll see it's really nice to have these 1 nearest neighbor results, because all you have to do is say, okay, what's this thing, y? Okay, y. What's the closest thing to y? 11. Okay, well, 11 must have been an angel. Very easy to read off. Okay, so these ones are really nice. You want to have lots of these. They help you out a lot. Okay. The next thing you want to look for, in my opinion, you can do this anyway. You could start saying, well, what about 5? Let's look at 5 now. Or you could say, you know what? I really want to consider what happens to z. What's z? You could do it any ordering you want, but some things you won't be able to answer right away. So the way I like to approach the problem is to always do the 1 nearest neighbors first, because you can get some answers straight away. Because if there's any of these entries filled out, you can immediately fill out some stuff over there. And the next thing is look for things that change between 1 nearest neighbor to 3 nearest neighbors. If things didn't change, the other 2 out of these 3, because we know one of them, the other 2 that inform this 3, I mean, it's kind of hard to say. It could have been 1 and 1, or it could have been both. But if something changed, then both of the 2 guys we included must have been the thing that this thing wasn't. Sorry, I'm saying that terribly. But let's look at, for instance, x. Or, sorry, y. So y changes its classification from 1 to 3, what we think it should be classified as. And so we can see y is closest to 11, 7, and 9. But we know that 11 was a plus. But when we considered 3 of them, we put y as a minus, which must mean the other 2 must be minuses, because we're taking a majority. So what are the other 2 things? Well, it must be 7 and 9. Those 2 things must be minuses. So we can go ahead, write 7 and 9 as minuses. Okay? Cool, cool. So now we can keep going. And this becomes more of an art at some point. So we can see here, okay, anyone see something we could do? Maybe let's look at 10, Z, 8, 9. Okay, so what about this 10 and this 8? Do we know anything about them? Well, they're close to Z, so let's look at Z. Z is a minus of 3. And we don't even know anything about it for 5 or 1. And this is already a minus. So there's there's a bunch of things these 2 could be. It could either be they're both minuses, or one of them could be a plus and one could be a minus. Can't really tell. Okay? And actually, you won't ever be able to tell for these. You can keep going and figure that out, but you can also say, like, well, no one else is being informed by 10 or 8. Like, everyone else has 5 closer guys than that. So 10 and 8 are only affecting Z's values, really. So let's put 10 and 8 as just unknowns, because we don't know those. All right. Okay, so what about x for 5? X changes when it goes to 5, right? Maybe W is better to look at. W has 3, 4, and 6. Oh man, totally forgot the right. Yeah, these get like pretty tricky of like what to do next. Does anyone see something we could do? So maybe it's just that these matter a lot, like how close the things are to each other when you draw them. So they'll draw them really nicely, but I just didn't draw them very nicely this time. Okay, let's see here. Y, 7, 9, 11. We got those. B. Okay. Z. Did I forget one? 3, 4, 6. Okay. Okay, here's something we can do. When W had 3, it was, oops, it should be a plus. It was an angel. But then when W was 5, when we considered 5 closest guys, it switched. So there we go. This thing switched from 3 to 5. So both of the guys that were included in 5 must have been minuses. That's the only way you can cause a switch. Okay. So let's see, out of the 5 closest guys to W, the 2 furthest must be minuses. So we can see, okay, these are like the 3 closest. This is the next closest. Oh, 5 is probably a minus then. That's what it looks like, I guess. So let's see here. So we can do that. And then we can see that if W was plus there, but the 5 closest guys were 7 and 5, one of these guys must be a minus, and 2 of these guys must be a plus. Oh man, I'm totally getting stuck on this one. Yeah, so I probably just didn't draw it quite to scale. That's what's going on. Oh, Oh, okay, there we go. So x also changes going from 1 to 5, but we've got two close guys to x being minuses. So the other three have to be pluses. That's the only way that we'll consider 5 things close to x as being a plus. So now we can look up here. We can say 2, 3, and 4 are pluses, which means that, did I miss one? 2, oops. 5 is a minus. Okay, and we've got pluses and pluses for w. Switched. So 6 must be a minus. That's the only way that w could have switched from plus to minus, is it needs 3. It needs 2. Needs 3 minuses total, but it already had 2 pluses, so the other 3 must be minuses. So that's why I got the 6 to be minus. Now we fill this whole thing out. Sorry about that, guys. Yeah, just I guess I wrote an A there and I got confused, but yeah, the way you want to look at it is whenever things change, that's like an interesting point to start considering. All right. Cool. So they ask you all of that, and then they ask you, okay, now let's classify V. Okay, so now we've figured out what all of these points were, 1, 2, 3, all the way to 11, except we haven't really figured out 8 or 10. Let's classify V. So now that we know all the things, ignore X, Y, Z, and all those guys. Only look at the number ones, and now let's do V. So V is really close to 9, right? So for 1 nearest neighbor, V is just going to be a minus. For 3 nearest neighbors, I'll tell you guys which are the 3 closest, because I probably just drew it off by a little. The 3 closest are 9, 10, and 11. 9, 10, and 11. So unfortunately, this is a minus and this is a plus, so it depends on what this 10 is. But we don't really have any information on 10. So we actually don't know. This is an unknown. We don't know what we would classify with 3 nearest neighbors. And for 5 nearest neighbors, this is actually a really tricky one. Okay? So the 5 closest guys are 7, 8, 9, 10, 11. So does anyone have a guess for what we would do if we looked at 7, 8, 9, 10, and 11? How we would classify it? Plus, minus, or U?
B minus.
So why not U?
Because okay. So if the 3 nearest neighbors for Z is a minus, so we know that Z's 3 nearest neighbors, which are 8, 9, and 10, come up to a majority of minuses. And considering that 10, 7, and 11 are also a majority of minuses, then we have a majority of minuses.
Yeah, basically what we can notice is one of these 2 must be a minus. And then we got that from this Z. So this is really tricky. We actually, the solutions accepted U, because if you just looked at these results, you'd say, well, what if these were both pluses, then it could be a plus. If they were both minuses, the minus, we don't know, U. But actually, if you remember, when we did the Z, really we do know something about this 10 and this 8. One of them has to be a minus. And so now when we do this, at least one of these 2 is a minus, so now we have a majority of minuses. And so this actually is a minus. That's the right answer. Okay, so that's a tricky one. But remember that in these solutions, they did accept U also. So if you forgot that, it's not a huge deal. Just a very, you have to know it really well to get that last point. All right, so that's that. I think the only thing I didn't cover was drawing boundaries for, we only expect you to draw boundaries from k equals 1 for nearest neighbors. Drawing boundaries is a little hard, so I would encourage you guys to look it up. It's like, it's easy, but it's really error prone. So just be on your game for that. And that's it. Also, if you guys didn't get your test back, you guys can meet me on my office hours on Friday, and if you can, otherwise email me, I can get it back to you. Yep.